start chapter number 7, which is about first and second order transient circuits. So, in circuits with inductors and capacitors, voltage and currents cannot change instantaneously. As we have discussed in chapter number 6, that in case of capacitors, the voltage across capacitor does not change instantaneously. That is, voltage across capacitor at time 0 minus will be same as we see at 0 plus. And in case of inductors, the current through inductor at 0 minus is same as I of L, that is current through inductor at 0 plus. That is, the current in case of inductor is continuous, while voltage across capacitor is continuous in case of capacitors. So in this chapter we are going to talk about first order circuits and second order circuits. So when we say first order circuits, these are the circuits that contain a single energy storage element. These energy storage elements could be a capacitor or an inductor. And the second part of this chapter would be about second order circuits, and these are the circuits where you have two energy storing elements, and these two elements could be two capacitors, two inductors, or a capacitor or an inductor. So let's talk about the analysis of linear circuits with inductors and capacitors. So the conventional analysis using mathematical models require the determination of a set of equations that represents the circuit. So up till now we have seen different techniques like nodal analysis, mesh analysis, in which we were required to find a set of equations. By solving those set of equations, we were able to find voltage or current in any resistive circuits. So for example, in nodal analysis or loop analysis of a resistive circuits, we actually get a set of algebraic equations, as we can see in this example. So for example, here we can see we have a resistive circuit. We have two current sources, and we have these three resistors that are connected in this way. So if we apply nodal analysis in this case, for example, here we can apply nodal analysis on node 1. So let's see, if we apply the nodal analysis, let's apply KCL at node 1. So current entering the node is I of A, which we have written over here, and the current leaving the nodes are these two, and we can see current leaving in downward direction is V1 over R1, and we know that 1 over R1 is the inverse of resistance is conductance. So G1 V1 is the value of the current. So G1 V1 is current going in downward direction, and current going in this direction will be V1 minus V2 over R2, and R2 could be replaced, 1 over R2 can be replaced by G2. So it would be V1 G2 and V2 G2. So we can see that G2 V1 can be written here, and minus G2 V2 can be written here. So this equation we have got by applying KCL at node 1. Likewise at node 2, if we apply KCL, we will get this set of this equation. So by solving these two equations, we can see we have two unknowns, that are V1 and V2, and rest of the values are known. G1, G2, G3, IA and IB all are known in any similar circuits. The only thing we need to find is V1 and V2. And now by solving these two linear equations, we are able to find the value of node voltages V1 and V2. And as we have discussed in nodal analysis, once you know the node voltages, you can find any voltage or current in any circuit. So, but when there are inductors or capacitors, the model become linearly ordinary differential equation. So in resistive circuits, we always end up with a linear equation, but whenever there is energy storage element or like capacitor or inductor that is introduced in a circuit, the equation is no longer a linear equation. Instead, you get a linear ordinary differential equation, which is also known as ODEs. So in this case, we need to have all those tools that we have seen so far for resistive circuits, and by using those tools, we will be able to analyze circuits with energy storage elements. So a method based on Thevenin will be developed to derive mathematical models for an arbitrary linear circuits with one energy storage element. So in this particular case, what we are going to do is we are going to use the Thevenin and Norton approaches that we have studied for resistive circuits to actually solve these kind of circuits where we have one energy storage element. So we will also look at a general approach that can be simplified in some special cases. We will see that the analysis in these cases become a simple matter of determining some parameters. So we will see that we are going to define a set of rules which we are going to follow to solve these circuits with one energy storage elements, and we will see that once we have developed those set of rules, all we need to do is find certain parameters to actually get the required answer. So two such cases will be discussed in detail for the case of constant sources, one that assumes the availability of differential equation, and a second that is entirely based on elementary circuit analysis. But it is normally longer. What does it say is that we are going to look at two different approaches. One is a step-by-step approach in which we are going to follow a certain series of steps that will allow us to find out the required voltage or current in a circuit, and the second one is where we are going to determine the differential equation first, and then we are going to solve that differential equation to find out the required answer. We will see both the methods in detail in this lecture. We will also discuss the performance of linear circuits to other simple inputs as well. And at the end, we will see what if we don't have a constant source as it is mentioned over here. So if we have a source that is changing, for example, there is a source that provides certain input at one time interval, and at another time interval the value actually changes, and what will happen to the circuit in that case. So we will see some other simple inputs and we will see how the circuit would behave in that case. Okay, let's have an introduction. We know that inductors and capacitors, they can store energy, and under suitable conditions this energy can be released. The rate at which the energy is released depend upon the parameters of the circuit connected to the terminals of the energy storage element. What this mean is कि आपके पास किसी भी सर्किट में अगर कोई कैपेसिटर या इंडक्टर लगा हुआ है, that element is able to store energy, and the rate at which that energy is released depend upon the elements that are connected with that energy storage element. For example, अगर यहाँ पे हमारे पास एक कैपेसिटर है, ये कैपेसिटर किस रेट से डिस्चार्ज होगा ये डिपेंड करता है किस किस्म का रेजिस्टर इसके साथ कनेक्टेड है at a given time. So depending upon the elements that are connected with that energy storage element, the rate of discharge will be decided according to that. तो ये इसकी डिटेल हम इंशाल्लाह नेक्स्ट स्लाइड्स के अंदर जाके देखेंगे कि ये डिस्चार्ज रेट हम कैसे फाइंड आउट करते हैं. यहाँ पे हमारे पास एक एग्जांपल है एक कैमरे की फ्लैश की. हम अगर एक कैमरा यूज़ करते हैं तो हम देखते हैं कि व्हेनेवर वी टेक अ फोटोग्राफ विद अ कैमरा जिसके ऊपर एक फ्लैश लगी हुई हो, द मोमेंट यू टेक द पिक्चर आपका फ्लैश जो है वो चलता है, और उसके बाद इट टेक्स लिटिल वाइल टू चार्ज दैट फ्लैश अगेन, एंड देन अगेन यू व्हेन यू प्रेस द बटन आपका नेक्स्ट पिक्चर जो है वो आप लेते हो. तो दैट phenomena or that process is actually modeled using this circuit. Here we can see this is the battery that is connected with the capacitor with this resistor at this time. इस टाइम पे ये स्विच इस टर्मिनल से कनेक्टेड है, इस टाइम पे ये वोल्टेज सोर्स जो है इस कैपेसिटर को चार्ज कर रहा है. सो द मोमेंट यू प्रेस द बटन ऑफ योर कैमरा, this switch will be connected to this terminal, and now this battery will be disconnected, and the charge stored by this capacitor will be released to this resistance R, and this R is the xenon lamp जो कि हम कैमरे के फ्लैश को मॉडल करने के लिए हम यूज़ कर रहे हैं. और उसी इंस्टेंट पे जो एनर्जी आपके इस कैपेसिटर ने स्टोर की हुई होगी, इट विल बी रिलीज टू दैट द लैम्प, एंड द मोमेंट यू आर गोइंग टू लीव द कैमरा बटन, तो आपके पास दोबारा ये स्विच जो है ये इस सोर्स के साथ कनेक्ट हो जाएगा, एंड अगेन the capacitor will start charging itself, and once it is fully charged and you press the button, ये switch दोबारा connect हो जाएगा इस terminal के साथ, and that energy stored by capacitor will be delivered to this resistance. So this circuit actually depicts how a camera flash actually works. So with the switch on the left, currently in this position, the capacitor receives charge from the battery, and once this switch is connected to the terminal on the right, that energy stored by this capacitor will be delivered to this load, which is a lamp. So when switch is on the right side, this is how the circuit would look like. The energy stored by the capacitor will be delivered to the xenon lamp. So this is how the charge and discharge cycle of this capacitor would normally look like. So initially, when the capacitor is fully charged, when the switch is connected to this terminal, we can see this voltage that is connected to it. This energy will be available to this capacitor, and this is the amount of energy that will be stored by that capacitor. Say for example, the voltage across capacitor will be V naught, and the moment you press the button and the switch is connected to this terminal, the energy stored by this capacitor will be delivered to this charge. So here we can see the voltage across the capacitor will drop with this rate. So this will be your discharge time, which is defined by this. And once the camera has flashed, उसके बाद दोबारा ये जो स्विच है ये पोजीशन लेफ्ट पोजीशन पे आ जाएगा, एंड देन द battery will start charging the capacitor, and here we can see the charge will be start accumulating in the capacitor, and the voltage across the capacitor will be increasing like this. So this would be the time required to fully charge the capacitor, which we call as the charge time. And then once the capacitor is fully charged, the voltage across this will be constant, will be according to V naught. And again, once the button is pressed, the capacitor will again discharge. Here we can see this is how the capacitor will discharge itself. So this would be again the discharge time. So this graph actually tells you how the charge and discharge of the charge of the capacitor actually takes place. So the capacitor would take a certain amount of time to charge itself, and then once you press the button, the capacitor will discharge itself to the load resistance. So how do we solve circuits with one energy storage elements? So as we have said, all those circuits which have one energy storage element, either could be a capacitor or inductor, they are known as first order circuits. So how do we solve first order circuits? We actually make use of the differential equations, and once we have developed the differential equation of the circuit that is given to us, we compare it with the standard form of the first order differential equation. And since we know the solution of the standard first order differential equation, we can determine the solution to our differential equation as well. So including the initial conditions, the model of a capacitor voltage or the inductor current will be shown to be of this form. तो हमारे पास जब भी हम कोई सर्किट सॉल्व करेंगे जिसके अंदर एक एनर्जी स्टोरेज एलिमेंट कनेक्टेड होगा, वी विल सी दैट उसकी जो इक्वेशन है इट विल लुक समथिंग लाइक दिस, और उसकी एक इनिशियल कंडीशन होगी विच विल बी डिफाइंड लाइक दिस. X of 0 plus means this is the initial condition, and that value would be some constant x of naught, and the equation itself would look something like this, where this x of t could be voltage across capacitor or it could be current through inductor. So since हमारे केस में हम बात कर रहे हैं कांस्टेंट वोल्टेज सोर्सेज की, तो इस इक्वेशन के अंदर ये जो f of t है, दिस इज द फोर्सिंग फंक्शन which defines the input function to the circuit. And since in our case हमारा जो सोर्स है वो एक कांस्टेंट सोर्स है, हम इस f फंक्शन ऑफ ये जो एक फंक्शन है विच इज़ ए फंक्शन ऑफ टाइम, इसको एक कांस्टेंट वैल्यू से रिप्लेस कर सकते हैं. लेट्स कॉल इट एज f थेवेनिन. और जितने भी वेरिएबल्स हमारे पास जो कोफिशिएंट्स हैं अलॉन्ग विद दिस, हम इन सबको यूनिट कन्वर्ट कर देते हैं. तो यूनिट के लिए वी डिवाइड ऑल द वैल्यूज बाय a, so that we make sure that we have one with the as a coefficient along with x. So whatever you will have as a coefficient next to this derivative will be a variable tau, and we will see what this tau is, and the initial condition will be defined like this. So whenever we are going to solve a circuit which is a first order circuit, our intention is to develop an equation which is of this form: tau dx by dt plus x, which is equal to the forcing function, and we also require the initial condition. So if we are able to determine these two values, we can find the answer to that problem, because we already know what is the solution of this particular problem. And once we know the equation of the circuit, we will directly find the solution to the differential equation. We will see how we actually do that in this case. So solving the differential equation using integrating factors, one tries to convert the left hand side into an exact derivative. So now what we are going to do is we are going to try and see what is the solution of this particular equation. You don't need to actually derive the solution yourself. You just need to apply the solution. What we are going to do is we are going to just talk about how this solution is actually obtained, but you don't need to actually memorize this derivation. So the first thing we do is, in order to solve this differential equation, we multiply and divide both sides by 1 over tau into e raised to power t by tau. We'll end up with this expression. So here we can see this 1 over tau will be cancelled with this tau. You'll only left with this expression. This whole term will be multiplied by this x, and this whole term will be multiplied by the right hand side. So in this case, we'll end up with this expression, because we know this part of this expression is nothing else but the derivative of this function. You can verify it yourself though. So you take derivation by parts. So you take the derivative of first, leave the second as it is, then you take the derivative of the second and leave the first as it is. So you'll end up with this expression. So this is the derivative of this function, and this part is nothing but this expression. So now we take integration on both sides. This derivative will be cancelled, and you apply the limit, you will end up with this expression. And on the right hand side, when you take the integral, you'll end up with this expression. Here we can see this f Thevenin, it's not a function of x because this is a constant value. We can take it out. So before that, we can multiply and divide by this function on both sides. We'll end up with this expression. So this variable, this function when multiplied with this, bases are same, powers will add. So e raised power 0 will be 1. You will left with x of t, and this term will go on that side. It will become this expression that you have over here, and this integral will be defined over here. It's just a mathematical manipulation. So this expression allows the computation of the response of any forcing function. We will concentrate on the special case when the right hand side is a constant. So basically ये जो expression आपके पास आ रही है, this is the solution of this differential equation. So whenever you want to find the solution of that differential equation, you can find the solution x of t of this differential equation by solving this equation. So since the forcing function in our case is not a function of time, we can take it out because it is a constant value. This tau is the value that you have over here, and this tau is known as the time constant, and this time constant is the factor that tells you how quickly a capacitor or inductor will charge or discharge itself. And the initial time t naught, this variable t naught is arbitrary. The general expression can be used to study sequential switching. So initially we will see that we will be interested in finding out the response of the circuit for t greater than equal to 0. So the initial time t naught in our case will always be 0. But later we will see that sometimes we have to see the response of the circuit when we have sequential switching. So maybe we have a constant input at time t is equal to 1 second, and maybe at time t is equal to 5 seconds we turn off the switch, and in that case the response would also change because the input has changed. So in that case we might have to look at the general expression of this solution, but for now we will assume that the initial time t naught is equal to 0. So far we have seen this is the differential equation that we are interested in finding out for all the circuits, and initial condition that is required in all cases. And the solution of this differential equation is given as this expression over here. So let's see how we can find a closed form expression of this solution. So since the right hand side is a constant, so f Thevenin we can take it out because this value is a constant value, it can be taken out. So we'll end up with this expression, and here we can see कि आपके पास ये जो expression दिया हुआ है, because the powers are being added, हम इसको divide कर सकते हैं दो exponentials के अंदर, और इसके अंदर ये जो element है, this is a constant element because we are only interested in the variable x. So हम इस वाली term को भी बाहर ले आते हैं and we'll end up with this expression. और अब हम जब इस integral को solve करेंगे, we'll have this solution and this will be the range that we'll apply. So once you have applied the ranges, the whole expression will reduce down to this expression over here that we can see. So here what we can do is, if you look closely, this exponential, when it will be multiplied by this exponential, bases are same, powers will add. So e raised power 0 will be 1. So you will only be left with f Thevenin, which is representing the forcing function or the input voltage to the circuit. So this will be f Thevenin. This x t naught, which is the initial condition, and multiplied by this factor will be multiplied by this factor as well. So you will end up with this expression after substitution. So if we look at this expression, this is the solution or the closed form expression that is representing the solution of this particular differential equation. So in this case, what we do is we define the solution of this differential equation as x of t, and this x of t is valid for t greater than equal to t naught, and since we have assumed t naught to be equal to 0, so this whole expression would be fth plus x of 0 minus fth and e raised power minus t by tau, because this t naught is also 0. So the form of the solution will be like this. So this solution can be represented as this. So in this case we can see this k1 is nothing else but the forcing function, which is the value of the source. K2 is basically the difference of the initial value and the forcing function. So if we are able to find the equation of the circuit in this form, we can see whatever you will have over here will be your k1, and the coefficient of the derivative will be your tau, and since you know the initial condition, x naught minus f Thevenin will be your k2, which is this one. So you just need to find out the values of k1, k2 and tau to find out the solution x of t, which is the solution of this ordinary differential equation. So in all cases, you are required to find out these three variables to find out the solution of any ordinary differential equation. So in this solution, this part is known as the transient solution. This is the term that actually allows you to determine the natural response of the circuit, and this part of the circuit, this part of the equation, it is the forced response, or it is also known as the particular solution of the differential equation. So this tau is the time constant that we have set. So any variable in the circuit can be of this form. So if you are interested in finding out the voltage across capacitor or current through inductor, all the solutions will be of this form. And we are interested in finding out K1, K2 and tau. So this will be our required answer in all cases where we are dealing with first order differential equation. So we are interested in finding out K1, K2 and tau. So this is all what is required in this case. So let's talk a little bit about the transient response, which is also known as the complementary solution. So all the solutions that we will see will, as we have said, that will always be of this form. X of t will be equal to k1 plus k2 e raised to power minus t by tau. So this is known as the particular solution, which is known as xp of t. This is because of the forcing function that you have over here. And plus this part of the solution is xc of t, which is also known as the complementary solution or the natural response of the circuit. So you get this solution when you consider the forcing function to be equal to 0. So when the forcing function is equal to 0, it means the circuit will behave in a natural way. The way, for example, it has stored certain energy, it will release that energy to the circuit in a natural way. There will be no forcing function that will be involved. So in this case, the total solution x of t will be the sum of particular solution and the complementary solution. So if we talk about the transient response or the complementary solution, this exponential actually tells us a certain information, and that is about the time constant, because we can see this expression depends upon tau. So if you look at this solution xc of t, if we vary t from 0 onwards and look at the value of the complementary solution, we can see when t is equal to 0, this exponential will be e raised to power 0 is 1. The value is k2. If we put t is equal to tau, we can see e raised to power minus tau by tau is e raised to power minus 1, and e raised to power minus 1 is 0.368 k2. So here we can see the value has reduced almost 63.2%. So after one tau or one time constant, the value of K2 will reduce by 63.2%. And if we keep on plotting this function for different values of tau, we will see that between any two intervals from tau to 2 tau, we will see the value will again further reduce by a factor of 63.2%. And after 5 tau, you will see the value has reduced to more than 99%. This shows that any circuit that is having a natural response, the value of the natural response will reduce to almost 0 after 5 time constants. So this is what is discussed over here. The initial value is dropped by 63 to 63.2% of the initial value in one time constant. And we can also see, if we plot the function like this, the tangent from the initial value will always intersect at one time constant. So depending upon the value of tau, you will see that the behavior of the circuit will depict how fast or how slow it is discharging or charging. And we can see that after 5 time constants, the complementary solution or the natural response is 0.0067 K2, which is less than 1%. So after 5 time constants, we can say the complementary solution is almost 0. So the overall solution x of t will be nothing else but the particular solution only, xp of t, because this variable will be almost 0. So let's see what is the effect of the value of tau. What if the tau is a big value, or tau is a smaller value? So if you look at this exponential, we can see if you have tau which is a smaller value, you can see the value of this function reduces to 0 at a much quicker rate. You can plug in the value of t, and considering tau is equal to 0.5, you will see, for example, if t is equal to 2, you can see e raised to power minus 2 by 0.5. This is e raised to power minus 4. And you will see, if you find out this value, it will be very close to 0. Or in other case, if tau is equal to 4, for the same value of t is equal to 2, you will have e raised to power minus 4 by, minus 2 by 4. That is e raised to power minus 0.5. And if you find out the e raised to power minus 0.5, you will see the value would be somewhere over here. So this shows that if tau is a smaller value, the circuit will discharge very quickly, and if the value of tau is larger, the circuit will take more time to discharge itself to become equal to 0. So the complementary solution will reach 0 at much later. So as we have seen that after 5 time constants, the value of complementary solution will become less than 1. So if tau is equal to zero point 0.5 seconds, 5 tau means 2.5 seconds. So the value of the value of complementary solution will become 0 after 2.5 seconds, which we can see over here. At 2.5 seconds, this curve has reached 0. But in this case, when tau is equal to 4, 5 time constant means 5 fours are 20. So after 20 seconds, this graph will reach 0. So the value of tau actually tells you how quickly the transient will disappear, in any circuit. If the time constant is a large value, the transient response or the natural response will die at much slower rate. But if tau is very small, the transient response will disappear much quicker. So let's look at the how do we determine the time constant value. And in this case, let's look at an example where we have a voltage source, a capacitor, and a resistor, and a capacitor connected like this. So this voltage source is actually charging the capacitor. We will see how this at what rate the capacitor will be charged or discharged in this case. So we are going to find out the value of the time constant. So in this case, let's apply the KCL at this node. So let's say current going in this direction will be, the voltage at this terminal is VC, the voltage at this terminal is Vs. So it would be Vc minus Vs over Rs, current going in this direction. Current going in this direction will be C dV by dt, because we know that the current through capacitor is defined as C dV by dt. And because some of all the currents leaving the node are defined, we can write the KCL equation like this. And from this, we can derive the equation which is the generic form of equation that we require, that is tau dx by dt plus x is equal to f, and we need the initial condition which is x naught. So this is the desired equation that we need to get. So in this case, if we solve this a little bit, we'll end up with this expression. So here we can see whatever you have as a coefficient with the derivative, that is your tau. Whatever you have over here is your f, and your x is this function VC. So this VC is your x. So we can directly see this value of tau depends upon R Thevenin C. So this R Thevenin is basically this resistance, and this C is the capacitance of this capacitor. So if we have got this differential equation, we can directly find the solution of this circuit. That will now be Vc of t will be k1 plus k2 e raised to power minus t by tau. So we need to find what k1, k2 and tau is to find out the voltage across capacitor. So but we have got the standard form of the differential equation that we require. So in this case, tau is R Thevenin C, and since and in this case we assume that Vs is equal to voltage source. This is the voltage source, and the initial voltage across capacitor at time t is equal to 0 is 0. Let's assume the second information that we require, that is x of 0 plus is x naught. This is the information that we require. So we assume that this value is equal to 0. So in this case, the solution will be equal to this. So we know that solution K1 is equal to F Thevenin, which is V Thevenin, which is Vs, and we know that K1 plus K2 is equal to X of 0 plus, or we know that this is V of 0. So K1 is Vs plus K2. So this means K2 is equal to V of 0 minus Vs. And since V of 0 is 0, K2 is equal to minus Vs. So you plug these values in the standard solution, that is Vc of t is equal to K1 is Vs plus K2 is minus Vs e raised to power minus t by tau. Tau is Rc. So this negative will come out, you will end up with this expression. So this is the solution to this circuit, where you are able to find the voltage across capacitor as Vs minus Vs e raised to power minus t by tau, and tau in this case is R Thevenin C. So this is how you solve this problem and find out the variables V1 and V1, K1 and K2, and the variable tau. So this part is the transient response, and for practical purpose the capacitor is charged when the transient is negligible. This means that after 5 tau or 5 time constants, this transient response will become 0, and the voltage across capacitor will be a constant value, which is Vs. So we will say that after the transient response is finished, the capacitor will be fully charged, and the value across capacitor will be same as the voltage source that is connected with it. And here it is also shown that if we talk about time, after 5 tau, the value of this transient, it reduces to almost 0. This is what it shows over here. So with less than 1% error, the transient is negligible after 5 time constants. And this is where we can see the effect of time constant. So here we can see this is the solution to this equation. So voltage across capacitor, assuming the voltage source is 1 volt, so it will be 1 minus e raised to power minus t by tau. So this is 1 minus e raised to power minus t by tau, and assuming if we have 1 time constant all the way up to 5 time constants, we can see if the time constant is a smaller value, the transient response will die quicker, and circuit will and the voltage across capacitor will quickly go to Vs. So here we can see the transient response is dying off quickly, and after 5 time constants, because tau is equal to 1, after 5 time constants, the output of the voltage across capacitor will reach the value of the source, which is 1. But as the time constant is increasing, it would take much longer time for the voltage across capacitor to reach the steady state, which is the voltage across which is the voltage of the source. So this actually shows you the effect of time constant in a circuit. The larger the value of the time constant, it would take much longer time for the circuit to reach the steady state. When we say steady state, we are actually saying that the transient response, when the transient response becomes 0, the response that is left is the steady state response, which is the this value K1. Okay, let's conclude the session here. In the next class, we are going to introduce you to the first approach of solving the first order differential equation in a first order circuits by solving the circuit using the differential equation approach. So let's conclude the session here. Thank you very much.